Okay, dear students, let us go ahead. In last lecture, we have proved this theorem that if K is a normal extension of F and if H is any subgroup of GKF, then and if KH is a fixed field of H, then this both equalities are true. So we proved the result for any H which is a subgroup of GKF. So for every subgroups of GKF, we have already proved the result. Okay, so if we take this H as GKF itself, that is GKF is a subgroup of GKF, right? So if we replace H as GKF, then what will happen to this equality? Dimension of K over KH. Now H is nothing but GKF, right? But okay, this is same as order of GKF. If I take H as GKF, then we have this, right? Uh, but because K is a normal extension, by definition of normal extension, this is nothing but F. So I'll get this as dimension of K over F, because this is same as F if K is a normal extension of F. So this theorem says that if K is a normal extension, then dimension of K over F is same as order of GKF. Okay, because the result is true for any H. So if I replace H by GKF, then I'll get this. So in particular, this theorem says that if K is a normal extension, then order of GKF is same as dimension of K over F. If you remember, in last theorems we have proved that, or in last theorem of unit 3, we have proved that order of GKF is bounded by dimension of K over F, right? For any K and F. If K is an extension of F, finite extension of F, then order of GKF is bounded by this. We have already proved this. But if K is a normal extension, then the bound becomes the equality. That is what we have proved. Okay. So if K is a normal extension, there is equality in this result, that order of GKF is same as dimension of K over F. Okay. So, and also here we can observe that KH is nothing but now F. So order GKF is same as GKF. So we don't get anything new from this second one, but the first one, from first one we will get that order of GKF is same as dimension of K over F. Okay, so now let us, now that we have seen that remark, now let's go to next theorem. Which I will give as an exercise, because this theorem is a very simple theorem and the proof is available with you. So take this as an exercise. I will just state the theorem because I need this theorem in the next theorem, which is the characterization of normal extension of F. So let K be the splitting field of f of x, which belongs to Kfx, and suppose Px is the irreducible factor of Fx, and let Px be the irreducible factor of f of x in capital Fx. Now, if the roots of Px are known, that is, if roots of this Px are alpha 1, alpha 2, and so on up to say alpha r, then for each I, there exists some sigma I which belongs to GKF, such that sigma I of alpha 1 is nothing but alpha I. So that means, okay, let us once again see the statement of the theorem. If K is the splitting field of a polynomial fx, and suppose this polynomial has an irreducible factor Px, and suppose these are the roots of this factor Px, then corresponding to this root we have sigma 1, such that sigma 1 maps alpha 1 to alpha 1. Corresponding to this root alpha 2 we have sigma 2, that is sigma 2 of alpha 1 maps to alpha 2, sigma 3 of alpha 1 maps to alpha 3, and so on. Okay, So this theorem gives us the existence of those sigma i's, guarantee of the existence of sigma i's belongs to GKF, which satisfies this property. So take this as an exercise, and we will need this theorem for the next theorem, which is nothing but characterization of normal extension of a field. Okay, so now let us prove this theorem. Prove that K is a normal extension of F if and only if capital K is the splitting field of some polynomial over capital. Okay, so let us prove this theorem. Start with the proof. We'll first assume that K is a normal extension of F, and then we'll show that K is a splitting field of some polynomial over F. That is, we will construct some polynomial whose splitting field is this normal extension. Okay, so assume that capital K is a normal extension of capital F. Okay, now we will construct a polynomial whose splitting field is this K. We'll construct a polynomial whose splitting field is this K. Now, because K is a normal extension, by definition K is a finite extension, and because we know that every finite extension is a simple extension. K is a simple extension, provided obviously characteristic should be 0, and we are assuming this fact that characteristic of the fields are 0 over here. Okay, so because K is a normal extension of F, K is a finite extension of F, and hence K is a simple extension of F, then capital K is a simple extension of capital F. That is, because K is a simple extension of F, there is some A in K such that f of A is same as K, right? Because K is a simple extension, this thing is true for some A belongs to K. Now, also we have order of GKF. See, as we have seen in the earlier remark, that K is a normal extension of F implies that order of GKF is same as dimension of K over F, right? So also order of GKF, we have seen this in remark. Okay? Order of GKF is same as dimension of K over, okay, and we know that dimension of K over F is finite because K is a normal extension of F, it is a finite extension of F. Okay, so order of GKF is finite. So let us assume the elements of GKF. Let the elements of GKF look like this. GKF be sigma 1, sigma 2, and so on up to sigma, say, n. Suppose the order is n. So there are n elements in GKF, and because GKF is a group, one of the elements should be identity. Let us, without loss of generality, assume that this is the identity element. Okay, this is the identity element. That is sigma 1 of A is equal to A for every A. Right. So now let us consider a polynomial or construct a polynomial. Now consider Px. I'll take Px as the polynomial, this one. Sigma 1 of A, x minus sigma 2 of A, and so on up to x minus sigma n of A. Okay, so I have, in constructing this polynomial, I have made use of this A and also the sigma i's. Sigma 1 of A, sigma 2 of A, sigma 3 of A, and so on up to sigma n of A. So we can see that this is a polynomial whose roots are sigma 1a, sigma 2a, and so on up to sigma n a. So if I consider elementary symmetric rational functions in the variables sigma 1a, sigma 2a, and so on up to sigma n a as alpha 1, alpha 2, and so on alpha n, then it is clear that we can write this polynomial. When we expand this polynomial, we have this thing x to the power n minus alpha 1 x to the power n minus 1 plus alpha 2 x to the power n minus 2 and so on. Here actually it is plus minus. So here plus, so minus, and so on up to minus 1 to the power n minus 1 alpha n minus 1 x plus minus 1 to the power n alpha n. Okay, where we know that what this alpha 1 is. What is alpha 1? It is sigma 1 a plus sigma 2 a and so on up to sigma n. What is alpha 2 a? Alpha 2 is nothing but sigma 1 a into sigma 2 a plus sigma 1 a into sigma 3 a plus sigma 1 a into sigma 4 a and so on. We know that this alpha i's are elementary symmetric rational functions in the variable sigma 1 a, sigma 2 a and so on up to sigma n a. Okay, you can observe that this equality is clearly true. For that, take n equal to 3 and simplify. Just open the brackets and you can observe that this thing is true. Okay, so where this alpha i's, what are these alpha i's? They are elementary symmetric rational functions. Okay, where alpha I are elementary symmetric functions. Symmetric functions of the variable sigma 1a, sigma 2a, and so on up to sigma n. Okay, so now this is our px. I will show that this polynomial is in fx. If you remember, in last theorem also we have constructed the same alpha i's. Okay, and there we were taking elements of h, capital H, as sigma 1, sigma 2 up to sigma h, and we have proved that sigma I of alpha j is same as alpha j. Okay, we discussed everything in detail in that theorem. So using the same argument or similar argument, here we are taking h as sigma, sorry, gkf. Okay, so in last theorem we have already seen taking h as sigma 1, sigma 2 and so on up to sigma h. Here we are taking gkf as sigma 1, sigma 2 up to sigma n, but the properties are same. So exactly same thing is true here also. So I will directly write then uh, by arguments similar to above theorem. Arguments, we have discussed these arguments in detail in last theorem. Okay, then by arguments similar to above theorem, the same arguments can be used here, similar about to above theorem. What we have is sigma I of alpha j is same as alpha j. So that means this alpha j's, all the alpha j's are fixed by every sigma i's, right? And therefore, what does that mean? Again, using arguments of above theorem, alpha j belongs to, there we used to write kh, but here instead of h we are taking gkf. So we have alpha j belongs to gkf. But because k is a normal extension of kgkf is same as f, right? By definition of normal extension. So what we have proved is every alpha j's are in f. So what we have proved, all these coefficients are in f. This is already in f, this is in f, this is in f. All these coefficients are in f. So that means our polynomial belongs to fx. Okay. So the polynomial that we have seen here or constructed here is a polynomial in fx. So thus let's write thus px polynomial is in fx. So we constructed a polynomial in fx, and actually what we have to do, we have to prove that k is the splitting field of some polynomial over f. So we have constructed this polynomial. Okay, we constructed a polynomial px. Now we will prove that the splitting field of this px is same as k. Okay, we will show that splitting field of this px is nothing but k. Let us see how we can do that. Okay, now already we can see that this sigma 1 of a is same as a because sigma 1 is the identity. Okay, so already a is the root of px, right? So now we have to find out the splitting field of px. I will show that the splitting field is exactly k. Okay, let us assume that the splitting field is some, say, jx. Okay, suppose splitting field of px is, say J, capital J, which is the extension of K, sorry, F. Okay, suppose the splitting field is some J. Then I need to prove that this J is same as K. Okay. Now because this J is the splitting field, it is the smallest field which contains all the roots. Okay, all the roots of Px. Now we know that A is already a root of Px, right? So J is the smallest field which contains A, but actually we know that K is nothing but f of A, and f of A is the smallest field which contains f and A, right? And J is a field which contains A. So that means K must be a subset of F. K must be a subset of J, because J field contains A, but K is the smallest field which contains A. So we can see that K is a subfield of J, right? But now you can see that all the roots of Px are of this form K. See, they are all in already in K. Why all the roots are in K? Because sigma 2a. See, sigma 2 is what? Sigma 2 is an element of GKF. Element of GKF means what? It's an automorphism from K to K. Okay. So sigma 2 of A, that will also lie in K, right? So all these are already elements of K, right? So K contains all the roots, and K is a subspace of J, right? So we must have K equal to J, because we assumed that J is the splitting field, right? So J is the smallest field which contains all the roots, but we have that K is the field which contains A as well as all the roots of Px, right? And K is also a subset of J because of this fact that K is the smallest field which contains A and J contains A. So K is a subset of J is already there, and J is a subset of K is there. Why? Because K is the field which contains all the roots, and J is the smallest field which contains all the roots. So combining these two inclusions, what we have is J is exactly same as K. Okay. Once again, I'll repeat why K is a subset of J, because of this fact that inside J there is A, but K is nothing but Fa. Fa is the smallest field which contains A, and J is a field which contains A. Therefore, K must be a subset of J. And now, why is J a subset of K? Because we already know that inside K all the roots of Px are there because of this fact. All the roots of uh, these are the roots of F, Px, right? And all the roots are already in K. But the smallest field which contains all the roots is J. So obviously J must be a subset of K. So combining these two, we have that J is equals to K. So the splitting field of Px is nothing but J. Okay, the splitting field of Px is nothing but J, and J is nothing but K. So what I have proved is splitting field of Px is nothing but K. So we constructed a polynomial whose splitting field is K. Okay? So I proved that K is the splitting field of some polynomial over F. Okay, that some polynomial is nothing but Px. So we proved that if K is a normal extension, then K is a splitting field of some polynomial. So one part of the theorem is done. So now let us conversely assume that K is the splitting field of some polynomial over F, and we will prove that this K is a normal extension of F. For that, we are going to use induction, but before that, we will see some things. Okay, so now we are starting with the converse part proof. Um, conversely, assume that K is a splitting field of some polynomial of some polynomial in Fx. Okay, and we will show that K is the normal extension of F. So our claim is to prove that K is a normal extension of F. Okay, we will prove this by using induction. Okay, using induction on what? Dimension of K over F. Okay, we will prove this by using induction on dimension of K over F. Our claim is to show that K is a normal extension of. So we will prove this by using induction. We shall show this by using mathematical induction induction on dimension of K over F. So dimension of K over F is nothing but a natural number, right? So we'll assume that the base case is dimension of K over F is 1. So in base case, we have to prove the result. So if dimension of K over F is 1, that is K is same as F, then can you see that the result is 2? Then actually the result follows. Why? Then the result follows. Why is this true? Because if K is F, then uh, if K is the same as F, then why? See, what we have to actually prove, K is a normal extension of F. If we are taking K equal to F, then why K is a normal extension of F? Because in that case, you can see that the definition of the normal extension is satisfied. What is the definition of normal extension? The first property is that dimension of K over F must be finite. It is actually 1, so it is finite, right? And the second property is that KGKF must be equal to F. Okay, this must be true. But we know that K and F are same. So FGFF. What is GFF? Collection of all those automorphisms from F to F, which fixes every element of F. Right? So GFF will contain only identity. GFF, collection of all those automorphisms from F to F, which fixes every element of F. That identity is the only element which fixes every element, right? So GFF will contains only identity. And whenever GFF contains identity, then what can we talk about FGFF? See, GFF is only identity. What is FGFF? FGFF is collection of all those elements of F, which is fixed by identity, right? Which is fixed by identity. But the identity fixes every element. So this is nothing but the whole F. Okay. So using definition of the normal extension, if K equal to F, then the result follows. So we have seen that the base case of the mathematical induction is true. So now let us put the induction assumption, induction hypothesis. What is the induction hypothesis? Assume that the result follows, or the result is true for, assume that the result is true for any pair of fields K1 and F1 with dimension of K1 over F1 is strictly less than n. Okay. So now we are assuming that the result is true for any pair of fields whose dimension over each other, or dimension of K1 over F1 is strictly less than n. That means what? K1 is a normal extension of F1. Okay. Suppose K1 is a splitting field of some polynomial or over F1, then the result is true that K1 is a normal extension. So here we are putting the induction. This is our induction hypothesis. Okay, this was our base case, and this is our induction hypothesis. Now we have to prove the result for n. So now we will prove the result for any K and F dimension such that dimension of K over F is n. Let us write those things. Assume that K is a splitting field of a polynomial of some polynomial over fx. Let us call that polynomial as small fx. Assume that K is a splitting field of polynomial fx belongs to capital Fx, and that dimension of K over F is n. Now we are proving the result for n. We have assumed that the result is true when it is strictly less than n. We have proved the base case 1. So now we will prove the result for n. Okay, so here we are assuming that k is the splitting field of some polynomial, say fx, and dimension of k over f is n. We have to prove that k is the normal extension of f. So let us assume that the irreducible factor of this fx is px. Okay, so let see, obviously k is the splitting field of f, and dimension of k over f is not now 1, because one case we have already settled. So here we are not assuming that n is 1. Okay, one case is already settled here. So splitting field k is not equal to f. So that means every root of this fx is not necessarily lying in small f. So that means this f has some irreducible factor. Okay, it has some irreducible factor over fx. Why? Because all the roots of fx are not in capital F. If all the roots of fx are in capital F, that means fx splits. That means there is no irreducible factor of degree larger than 1, right? But here, because k is not equal to f, all the roots of fx are not in capital F. That means this small fx has some irreducible factor whose degree is strictly larger than. So let us assume that irreducible factor as px. So let px be an irreducible factor of fx in capital Fx, and let us assume that its degree is r, with the degree of px same as, and let us see, because its degree is r, there are exactly r roots, right? And because all the roots of fx are in k, all the roots of px must also be in k, because the roots of px are nothing but roots of fx only, na? Okay, so let us assume the roots are alpha 1, alpha 2, and so on up to alpha r, and all these roots must be in k, because all this are the roots of f only, and the roots of f are in already in k. And this be distinct roots. Why I can write distinct roots here? Because of a previous result I can write this, that all these alpha i's are distinct. Why all these alpha i's are distinct? Because we have already proved that if characteristic of a field is 0, and if px is an irreducible polynomial, then px cannot have multiple roots. We have proved this result, right? So here we are already assuming that the characteristic is 0. This not need, we don't need to mention it. We are already assuming that the characteristic of the field is 0, and here px is an irreducible polynomial, so px cannot have multiple roots. That means all the roots of px are distinct roots. None of the alpha i's are same. It is clear that this is true, and also it is clear that what more is clear. Then it is clear that none of these alpha i's are in F. Why? Because if some of the alpha 1 is in F, then Px cannot be irreducible, right? Because if suppose say alpha 1 is in F, any of the alpha I is in F, then x minus alpha I is a factor of Px. So Px can be written as x minus alpha I into something say Qx. So that means Px has been reduced over Fx, right? This is in Fx, because if alpha I is in F, then x minus alpha I is a factor of px in fx. So that means px reduces over fx. But it is not true, because we are assuming that px is a irreducible factor in fx. In capital Fx, it is irreducible, so it can't split like this. If some of the alpha I is in f, then obviously it will get this freedom of splitting over capital F, which is not true, right? So it is clear that none of this alpha i's is in f. Okay, and thus what we can observe is that f is a proper extension, sorry, f is a proper subfield of f of alpha 1, right? Because alpha 1 is a element here which is not in F, because alpha 1 is not in F. So f of alpha 1 is a proper extension of F, because at least alpha 1 is there in f of alpha 1 which is not in F. Okay, so we can see that this is true. Okay, now our polynomial fx, it is in capital Fx, so obviously it should be in capital F alpha 1 of x also. Yes, because f is a subfield of f of alpha 1. So let us write, note that our polynomial fx is also in f1 of alpha, sorry, f of alpha 1 of x, right? See, now all the roots of fx are in K, right? So K is a splitting field of fx over f is true, and also over f of alpha 1 is also true, because the splitting field will not change if we change the field, right? So I can write that, and K is splitting field, because we are not changing the polynomial, obviously splitting field will not change. So K is the splitting field of f of x over f of alpha also, because we are not changing the polynomial, right? So the roots are not changing. We are just changing the base field. So splitting field is will remain the same. Now this is true that f of x belongs to f of alpha 1 of x, and K is the splitting field of this. And therefore, see now, see the situation of these three fields. F is a subfield of f of alpha 1, which is a subfield of K. So dimension of K over F is nothing but dimension of K over f of alpha 1 into dimension of f of alpha 1 over. So let us write that thing here. The dimension of K over f of alpha 1 into dimension of f of alpha 1 over f is same as dimension of K over f. And we know that dimension of K over f is nothing but n. So what we can observe is dimension of f of alpha 1, sorry, not dimension of K over f of alpha 1 is the same as dimension of K over f divided by dimension of f of alpha 1 over. So this must be strictly less than n, because this is already n divided by some number which is obviously larger than 1. Okay, this can't be 1. Why? Because if this is 1, then f is same as f of alpha 1, which is not true because of this. So this number is strictly larger than 1. So we are dividing n by some number which is not 1, which is strictly larger than 1. So obviously whatever this number is, it should be strictly less than n. Okay, so we can use induction hypothesis. What was the induction hypothesis? The result is true for any pair of fields K1 and F1, but dimension of K1 over F1 is strictly less than n. So we can use the result for this pair also. If we talk about this pair K and F of alpha 1, then the result is true, because the dimension is strictly less than n. The result is true for this pairs. That is, K is a normal extension of f of alpha 1. We can say, thus let us write by induction hypothesis. Induction hypothesis, K is a normal extension of f of alpha 1. And actually what we have to prove is K is a normal extension of f. So now we have to make that jump, that K is a normal extension of f. We already proved that K is a normal extension of f of alpha 1. So this may help us. This will in fact help us. Okay. Now, once again, let me just mention what my claim is. My claim is to prove that K is a normal extension of f. This is my thing that I have to prove. So in order to prove this, I have to prove two things. First, dimension of K over f is finite, which is already there, right? Dimension of K over f I am assuming as n, and it is already finite. So this thing is already done. Now what I have to prove, dimension KGKF. This is same as f. This is what I have to prove. Okay, dimension of KGKF is nothing but f. This is what I have to prove. But can you see that one thing is clear? F is always a subfield of KGKF. KGKF. Why? What is KGKF? Just observe. KGKF is all those elements of K which are fixed by every elements or every automorphism in GKF. And we already know that every automorphism in GKF is fixing F, right? Every automorphism in GKF is already fixing F. So you can see that F is a subfield of which KGKF, right? Once again, I repeat KGKF. What kind of elements are there in KGKF? All those elements which are fixed by every automorphism in GKF. But every automorphism in GKF is already fixing F. So you can see that F is a subset of this. Okay, so this thing is already there. So now what we are left to show? We are left to show that KGKF is nothing but subspace of F, subfield of F. So this is all because this is already there. In order to prove this, I just need to prove this. Okay, so actually now my claim should be KGKF is a subfield of F. Only this much is now remaining to show because already this is true and already this is true. If we prove this, then this is true and we are done. Okay, so now my claim just reduces to prove this that KGKF is a subfield of F. Okay, so this is the only thing that I need to now show, that KGKF is a subfield of. Okay, if I are able to prove this, then I'm done. We are done. Okay, so now I will start with one element here and I'll show that it is in F. So let us start with some theta belongs to KGKF. Okay, I will in the end of the theorem I will prove that theta belongs to F, and that will mark the end of my theorem. Okay, let us start with theta belongs to KGKF. Okay, theta belongs to KGKF. That means what? Theta is fixed by every automorphisms of GKF. Okay, so let us write that. So sigma will fix theta for every sigma which belongs to GKF. Every automorphism of GKF is fixing theta. That's why theta is in fixed field of KGKF. Okay, but can you see that this will imply that this is true? KGK, I am replacing F by F of alpha 1. Why is that true? The base thing for this is that GKF alpha 1. In fact, I will prove some more thing that if K1 is a subfield of K2, okay, then what is the relation between KK1? Let us write this as F1. If F1 is a subfield of F2, then what is the relation between GKF1 and GKF2? What is the relation? Okay, if F1 is a subfield of F2 and obviously both are subfields of K. So what is the relation between GKF1 and GKF2? Then this is the relation. Okay, though F2 is the extension of F1, but in case of GKF1 and GKF2, the inclusion is true. This kind of relation is there, right? Because if I start with an element here, that means an automorphism from K to K which fixes every element of F2. If an automorphism fixes every element of F2, then obviously it will fix elements of F1 also because F1 is a subfield of F2, right? So if I start with an automorphism, if I start with sigma belongs to this, so sigma is an automorphism from K to K which fixes every element of F2. An automorphism which fixes every element of F2 is automatically fixing elements of F1 also, because elements of F1 is a subset of F2. So if an automorphism fixes a larger field, then obviously it will fix a smaller field also. Okay, so every element in this is an element of this. So what we have proved, if F1 is a subfield of F2, then GKF2 is a subgroup of GKF1. Okay, so here now note, F is a subfield of F of alpha 1. Okay, so GKF1, GKF alpha 1 is a subgroup of GKF. So if something is true for GKF, larger group, if something is true for larger group, then the same thing is true for smaller group also, right? If something is true for larger group, then the same thing is true for smaller group also. If every element of the larger group is fixing theta, then every element of the smaller group is also fixing theta. I hope that this thing is clear to all of you. If any one of you have doubt in any of the theorem that I am discussing here, feel free to ask me personally. Okay. So sigma fixes every elements of this is fixing this also. Okay. Yeah. So that means every element of g, k, f of alpha 1 is fixing theta. That means theta must belongs to fixed field of g, k, f of alpha 1. That is theta belongs to k of g, k, f of, right? But I already know that f of alpha 1 is an sorry, k is a normal extension of f of alpha 1. So using dimension definition of normal extension, I can say that this is same as f of alpha 1. Okay, because here you just see that k is a normal extension of f of alpha 1. So fixed field of k, or because k is a normal extension of f of alpha 1, k is a finite extension of f of alpha 1, and k g k f alpha 1 is same as f alpha 1. By definition of normal extension, this is true. Okay, we have written this because f k is a normal extension of f of alpha 1. This thing is true. So my theta is now in f of alpha 1. So can you see that theta is of this form only, lambda 0 plus lambda 1 alpha 1 plus and so on up to lambda r minus 1 alpha 1 to the power r minus 1. You will think why I stopped at r minus 1 only. Okay, you will think, you should think why I stopped at, or why theta 0 looks like this, where all this lambda i's are from f. The question is why theta 1 theta looks like this. If theta is an element of f of alpha 1, why it looks like this? Okay, if I prove that every element of f of alpha 1 is of this form, then we are done, right? So actually this is true. F of alpha 1 is same as, it is collection of all these elements only, lambda 1 alpha 1 and so on up to lambda r minus 1 alpha 1 r minus 1, where this lambda i's are belongs to f. Every elements of f of alpha 1 is of this form. But why? That is the question. We know that f of alpha 1 is the uh, smallest field which contains f as well as alpha 1. So how must the element of f of alpha 1 look like? Uh, it should look like alpha 0 plus alpha 1, sorry, lambda 0 plus lambda 1 alpha 1 plus so on up to lambda n alpha 1 to the power n divided by, see, if you remember, we have already seen how the elements of f of a looks like. It looks like alpha 0, if I put a 0 plus a1 a plus a2 a to the power 2 and so on up to a n a to the power n divided by b0 plus b1 a and so on up to bm a to the power m, where this all ai's and bi's are from f, right? And n and m are elements of natural number n. We have already proved this, but under some special circumstances, we have proved that no need of this this denominator is there. Under some special circumstances, we have proved that this result is also true. And what is that result? If you remember, we have proved that in unit 3, that if, to be precise, I will mention the theorem, exact theorem, theorem 2.1.20. According to the numbering of my lecture note that I have, theorem 2.1.20 says that if A is algebraic of degree n over f, then dimension of f of a over f is nothing but n. In that result, if you see, we proved that t equal to fa, and that means fa is nothing but beta 0 plus beta 1 a and so on up to beta n minus 1 a to the power n minus 1. So at n minus 1 only we have to stop. Dimension of f of a over f, if it is n, then we have to stop at a to the power n minus 1. Okay, so using that theorem 2.1.20, we can say that f of a is of this form only. So you will think, in order to use that theorem, we must uh, prove that alpha 1 is algebraic of degree r over f, right? alpha 1 is algebraic of degree r over f. In order to use that theorem, we have to prove that alpha 1 is algebraic of degree r over f. That means I have to find out a minimal polynomial of degree r which is satisfied by alpha 1. Okay, but can you see, can you observe, I have an irreducible polynomial already, which is satisfied by alpha 1. And we know that minimal polynomials are irreducible polynomials. Irreducible polynomials are minimal polynomials. So I got a minimal polynomial which is satisfied by alpha 1 of degree r, right? So I can say from here that alpha 1 is algebraic of degree r over f, right? So using that theorem, because alpha 1 is algebraic of degree r over f, f of alpha 1 is nothing but beta 0 plus beta 1, alpha 1 and so on up to beta r minus 1, alpha 1 to the power r minus 1. Okay, so any element of f of alpha 1 will always look like this only. Okay, so actually what we have used is theorem 2.1.20. Okay, and in order to use theorem 2.1.20, we had to prove that alpha 1 is algebraic of degree r over f. That means we had to find a minimal polynomial of degree r which is satisfied by alpha 1, and that polynomial is nothing but px. So I hope that it is clear to all of you why I have written theta like this. Okay, so now because theta is of this form, now let us go ahead. See, now I will use the theorem which I have gave as an exercise. Okay, now I will use the theorem which I at the starting as an exercise. That if k is the splitting field of f of x, okay, and px is an irreducible factor of f of x, and if the roots of px are known, then there exists sigma belongs to gkf's which are of this form. Okay, we have all this set up in our theorem also. We started with a polynomial fx. We have that px is an irreducible polynomial of fx, and we have that alpha 1, alpha 2 up to alpha r are the roots of px. Okay, so everything that we have in our theorem is exactly the same that is there in the exercise. Okay, so I can use that theorem over here. So using above theorem, what I can say that there exists sigma i's, or we can find there exists sigma i's belongs to gkf such that sigma I of alpha 1 is nothing but alpha I for every I. Okay, so now see, sigma I is a member of gkf. Okay, so sigma I fixes every element of uh, sigma I fixes every element of f, right? So can you see that theta is same as sigma I of theta? Why is that true? Why is this true? That theta is same as sigma I of theta. Why is theta same as sigma I of theta? Let us see. Uh, sigma I, see from where we have started here. Theta belongs to kgkf, right? So every element of k, yeah, every element of theta is an element of kgkf. Okay, what is kgkf? Kgkf is those elements of k which are fixed by every elements of gkf, right? Because theta belongs to kgkf, uh, theta is fixed by every elements of gkf, right? So sigma i's are already in gkf, so sigma i's will fix theta, and so we are done. Okay, why this is true? Because sigma i's, because theta belongs to kgkf, right? And therefore theta is fixed by every elements of gkf. Sigma i's are already elements of gkf, so sigma i's will fix theta. So this is true. So now this is same as sigma I of, let us put the value of theta, and it is nothing but lambda 0 plus lambda 1 alpha 1 and so on up to lambda r minus 1 alpha 1, and that is same as If we split this, because sigma is an automorphism, we can split like this: sigma I of lambda 1. See, sigma I of lambda 1 is nothing but lambda 1. Why? Because sigma I is from GKF. That means sigma I is an automorphism from K to K, which fixes every element of F. Okay, and lambda i's are already elements of F. It is mentioned over here that lambda I is already an element of F. Okay, so uh, every sigma I will fix every lambda I. Okay, so this is nothing but lambda 1, and sigma I of alpha 1 is nothing but alpha I, right? Now second thing is lambda 2. Okay, lambda 2, and sigma I of alpha 2, alpha 1 is nothing but alpha 2 or alpha I, using this thing. Okay, and so on up to this is nothing but lambda r minus 1, and sigma I of alpha 1 is nothing but sigma I. Okay, so we have this, and this is also sigma I of lambda 0 is nothing but lambda 0, because lambda i's are element of F, and sigma I fixes every element of F. So sigma I of lambda 0 is nothing but lambda 0. So what we have observed is theta is same as lambda 0 plus lambda 1 and this and this and so on. Okay, so I can say that if I take theta here, then we have this is equals to 0. So now let us construct a polynomial QX. Now define, we are almost done. Okay, let us define QX like this. How we will define QX? We'll take QX like this polynomial. Lambda r minus 1, instead of alpha, uh, here we have some, here the power r minus 1 is there, and so here the power r minus 1 is there. Okay, here the power is, here also the power is 2. Okay, so this is lambda r minus 1. I am taking, instead of alpha I am taking x to the power r minus 1. So the second thing is lambda r minus 2 x to the power r minus 2, and so on up to the, this is lambda 1 x plus theta minus lambda 0. So I am taking qx like this. Then you can observe that q of alpha i's are 0, because if I substitute alpha I, then I will get this. So this is true for every I. Okay, so if I substitute alpha I, then you can see that we get this, which is nothing but 0. So you can see that q of alpha is 0 for every I. That means every alpha i's are the roots of qx. Okay, but so how many roots are there? There are total r roots, because alpha 1, alpha 2, and so on up to alpha r. How many roots are there? Total r roots are there. And what are the roots? Alpha 1, alpha 2 up to alpha r. And we know that already alpha 1, alpha 2 up to alpha r are distinct. So there are total distinct r roots of this qx. Okay, and therefore I can write qx as r distinct roots. Distinct roots. But what is the degree of qx? It is r minus 1. So how can a polynomial whose degree is r minus 1 have r distinct roots? That is not possible, right? That is possible only if it is a zero polynomial. Because a polynomial cannot have roots larger than its degree. That is fundamental theorem of algebra, right? That a polynomial of degree n can have roots at most n only. So how can a polynomial of degree r minus 1 have a distinct r roots? That is not possible. That is possible only if qx is 0. So therefore we must conclude from here that qx is 0. And qx is a 0 polynomial. That means what? Every coefficient of qx is 0. That means this is 0, this is 0, and that means this must be also equal to 0. That means theta 0 is same as lambda 0. Okay, and lambda 0 is already in F. So theta belongs to F, and we are done. If you remember what we had to prove, that every element of KGKF is an element of F. So I started with an element theta of KGKF, and I proved at the end that theta belongs to F. I proved that this is a subset of this, and so we are done. Okay. So I hope that this theorem is clear. to everyone. I have tried to explain every point of this theorem. So you can go back, because I will give this recording to you. You have the benefit of going back to the recording again and again. You can play wherever you have doubt. Okay? And if you still have doubt, then you can contact me in this